LiDAR, and communication devices. But also, we had to kind of looking at a much bigger kind of ecosystem with physical infrastructure and many type of vehicle, but also pedestrian, bicycle, right? So it's a complex, highly dynamic system. How do we actually secure that, right? So that's basically the kind of main challenge. And we believe we need to take a holistic and systematic framework to address the problem, right? So let's look at, for example, if you think about the system point of view, right? So you can think about what are the different components we have. We have vehicles and other road users, which is a component. We need to secure that individually also. And we have physical infrastructure, road transportation infrastructure with kind of camera LiDAR, but also just more kind of passive like road signs, etc. And then we have communication system connect everything. Then we talk about you have cloud computing infrastructure to support smart kind of mobility service running AI, etc. So how can we actually secure and harden each constituent systems, and then perhaps more importantly, to prevent some vulnerability that, say, a vehicle getting compromised, to propagate and threaten the entire kind of security of the entire system, right? So that's the kind of hard problem we kind of want to kind of tackle, right? So the other way you can think about the problem, all the system can consist of hardware and software, and there's having kind of long-standing research looking at how to actually harden hardware, software, right? So question, how do we actually leverage many existing defense mechanism technique to harden software and hardware? But more importantly, because of the system, right, communication interaction between different systems can be important, right? So the communication network provides an important role, and we also need to secure that. And part of the communication systems used to kind of exchange data. Right? So for example, you have to do cooperative perception, you need to sharing certain sensor data. How do we actually secure the data? And given that we have AI model running on the individual vehicles, physical kind of infrastructure, digital infrastructure, how do I could also protect the AI model, right? So that's the kind of hard problem. In particular, in this particular project, we have focused in particular on the latter, communication data, AI model. So if you look at the threat, this is kind of much more generic kind of, if you look at threat, right? So the hard part of doing security is you really have to think about who are the agents that actually can attack, right? So there's people that you can have criminals that maybe want to hack individual systems, steal information. But you also have organized crime and other, and you may have also nation-state adversary, right? So those kind of different actors, we need a different kind of approach to solving the problem. We need to understand the motivation and also what the capability and what is the likely impact, right? So this is the kind of problem we are facing. Oftentimes we can't really solve all security problem at one shot, right? So we had to make trade-off to secure things incrementally, but in a systematic manner. Right? So if you look at what are some of the interesting new threats happening, right? So again, because of we have this dynamic interacting system, if you look at autonomous vehicle, need to perceive the environment and make decisions. Attacker can manipulate the physical environment, for example, by changing, making some marking on the road sign, etc., that which can fool your AI system. And you may also have an attacker try to tamper with some of the sensors, right? So either having some kind of devices on the road that cause your LiDAR to malfunction, etc. Right? So those are the attacks we're interested in considering. And from the cyber aspect, right? So now you can have cyber, some in the middle, maybe actually try to inject the data into systems, especially if you think about vehicle-to-vehicle communication. You may have one vehicle maybe compromised, may actually sending falsified data to you, again, try to potentially kind of attack the AI system that is running on the individual vehicle, right? So those are kind of new type of attack we are kind of interested in looking at the address, right? So again, the attack not only going to just be on the individual vehicle, but could also attack on the infrastructure system, right? So all the kind of smart mobility service, intelligent transportation service running in the cloud, right? So we had to kind of consider this problem in a systematic manner, right? So that's the kind of overall kind of overview of the problem that we have looking at as part of the project, understand the whole from a systematic point of view, understand the different component and how we can secure them, what are the new threat model we need to worry about. And then we kind of start looking at how can we actually come up with a new approach. So one of the approach that we have come up with what I call the shared state approach. Again, because you have this distributed system that perceive the same environment, we have to share some information. And we need to make sure that the state information can be consistent. Right? So I'm going to use a particular example as illustration by looking at AV teleoperation pipeline. So this is some specific work we have looking at funded by National Science Foundation on the teleoperation side of how to actually secure this pipeline. Right? So that means it's going to the more specific, right? So the overall approach is you have a state that can share by a different entity. And this is important for cooperative kind of decision making, right? So this is recognizing the system itself is dynamic distributed, highly interactive, right? AV need to perceive the environment, interact with other object agent in the environment, for example, other vehicle, traffic signals, traffic sign, pedestrian, and make dynamic decision, right? In the case of autonomous vehicle itself, you may AI model running on the vehicle, but the teleoperation case, you also have a remote operator need to make decision. So same thing if you think about the intelligent control system, you have to have traffic light going to make decision dynamically based on traffic. And we had to kind of think about all the entity inside, right? So here, as a way we need to kind of think about the whole system-wide perspective, right? So we need to kind of ensure that state, all the entity that perceive the same environment, they need to be able to kind of maintain a consistent state and use that to kind of and make sure that stays into kind of protect the integrity of the state, right? So if someone tries to modify something, you're going to say, hey, by that we can actually see, hey, someone trying to manipulate the state, for example, modify some of the physical environment, you may actually detect there's an anomaly, or if the cyber attacker try to inject some data that is inconsistent with the state, right? So we can detect the anomaly, right? So those are the basic ideas we have. The key challenge here is how do you do it in a timely manner? So you can't really running a lot of heavy duty mechanism, take a long time to detect inconsistency or anomaly in the state that you perceive. That's not going to be sufficient, right? So we have to kind of work under the constraint of compute. You have limited compute resources on autonomous vehicle, on the physical structure, and the network constraint, right? You need to kind of have limited bandwidth and also the latency constraint. So using the example, the AV teleoperation, so here this is actually show a system we have built. We're using University of Minnesota's CAV vehicle. And we have instrument system make that remote drivable. We have built a pipeline so we can actually remote driving. So here show you the remote driving station. We have 3 camera, basically front and side, 2 of the side camera that we can use to do remote driving. And everything go over the 5G network. Right? So autonomous vehicle can stream camera data. In this case, it's actually we're not streaming LiDAR data because LiDAR consume too much bandwidth that today's 5G actually cannot accommodate in the uplink. So sending sensor data to the teleoperation, the teleoperation based on what it sees is going to send in command, for example, how to make turn or slow down because there's an object in front of you on pedestrian, you need to slow down. Right? So that's kind of the basic pipeline. The question, how do I actually protect this from someone in the middle, either, for example, in the 5G networks itself or in the broader internet, try to inject, for example, sending some kind of falsified video frame to you, to the teleoperation, try to attack your teleoperation. How do we actually prevent that one? Right. The problem is that we have to do that in a timely manner. We had to send a frame within like 100 milliseconds or less, right? So we don't have a lot of time to kind of do heavy duty. For example, one way you can provide some of the integrity is encrypt all the data, all the camera data, right? So the problem is you have large amount of data, and you encrypt the data to decrypt, you actually incur a lot of compute overhead. Right, so our approach is actually using a simple approach by encoding some watermarking directly in the video frame. Right, so this watermarking includes some kind of initial shared state when we establish connection, that we can use to synchronize the data. For example, each besides some random secrets, have the sequence number, we have the frame ID and timing information. What is the frame going to generate it, right? So GPL location of the state, we encode that data as a watermark and directly kind of embed it into the video frame as we transmit it, which then can be decoded by the teleoperation station to check for anomaly, right? So with these things, we also have the added benefit. Now we actually also have the timing information. We can actually feedback also the qualitative service, what the network and the qualitative experience from the application layer. So we can actually collect data so we know what to perform on the system. So as an example here, I should show you the video. We have a video to show you the system we have built. Right? So here, basically, if you look at the bottom here, which I highlight, we actually encode a lot of watermark, which contain the frame ID, sequence number, and the timing information and GPS location. On the other side, we can decode that. We also allow us to kind of plot and calculate the live latency as we drive around, right? So you can see the 5G network latency fluctuate. And this gives us a simple way to protect the system without resort to a lot of kind of encryption, heavy duty mechanism. So that's the piece, what we have done. I'm going to stop here. And we're going to transition to the next one, which I think Molly is going to take over.
Yeah, can you help me advance the slides?
Yeah, so.
Okay. Yeah, so
Molly, you can just let me know next. I'm going to click. Yeah.
Sure. Yeah, so I just want to, given the interest of time, so I want to just quickly mention again, we have the challenge with connected and automated vehicles, right? So it's autonomous vehicles, but there's that benefit of sharing data across vehicles so that you can improve the visibility and improve safety. So you have this intra-vehicle level security challenges, but then when you share data, actually the new challenge that emerges is that how trustworthy are those data? So next slide, please. So there is a general issue with or technical challenge with respect to adversarial machine learning. So autonomous vehicles heavily rely on ML algorithms to make various important decisions, for example, object detection. In this classic example where you can add small amount of perturbation that actually is invisible to the human eye, but as a result of that, the perturbation is created in such a way that can cause object misclassification. As you can see, start with Panda with less than 60% confidence of classification, but end up with Gibbon with more than 99% confidence. So this is just a classic example of adversarial machine learning based attack. Next slide, please. So what we have been focusing on as part of this project is looking at, next slide, please. Looking at perception, AV perception. How do we enhance AV perception? If you can advance next bullets. Yeah, so we have these time constraints of 10 frames per second, at least, with more than 20 frames per second desirable kind of rate. So as you can see, the real-time constraint is very real. So when you have data sharing across vehicles, you need to make sure that you meet that real-time constraints. Next slide, please.
Yep.
So I'm going to briefly talk about this project where we actually start looking at lossy networks. So in other words, how do we make this collaboration much more robust? And obviously, this can also be supported to address potential adversarial machine learning-based attacks. That is our ongoing work. But this Scorpion system builds the foundation on which we can design a much more robust in terms of spatial and temporal robustness for collaborative perception for autonomous vehicle data sharing, for sensor data sharing. Next slide, please. So this is just a motivation. I don't think I need to go into a lot of detail. There are classic examples of where you have occluded objects. With the help of collaborative perception, you can definitely get improved visibility, and similarly, sensors have limited range perception. So with sharing data, you can extend that perception range. Next slide, please. So, but obviously there are classic challenges with respect to sharing data. For example, there are spatial misalignments that are due to inherent sensing errors, or it could be just due to lossy networks, right? Because when you share a large amount of data, the network may not have sufficient bandwidth, and the vehicles themselves are moving, so they don't always have sufficient bandwidth to share a large amount of data that demand high bandwidth in a short amount of period of time. So, and similarly, when the data, sensitive data is collected, there are temporal misalignment. When you combine the data together, we have to worry about sensor synchronization challenges and the delay in transmitting data when they are merged together. So here are some examples which shows you the ground truth data when you do this data merging. And then subsequently, when you look at prediction, what is the predicted object location? And the main takeaway is that you can have spatial misalignment or temporal misalignment and temporal misalignment, and these can result in inaccuracy when you do sensor fusion, combining data from multiple systems. Next slide, please. So here is another illustration of where these kind of errors can occur, and these can be caused by both localization and synchronization errors. So this is just an example of using LiDAR data to show you where the misalignment can cause the location. Blue is the ego point cloud, and red is when you get data from remote data from nearby vehicles. Next slide, please. So given that challenge, we are looking at how do we ensure that when you combine data from nearby vehicles, you can still get the benefit despite those kind of lossy network challenges and as well as synchronization issues. So here are examples where as the network loss rate increases, as you can see that with different setup, with average precision for object detection, it severely degrades, right? So higher network loss rate, it shows that the accuracy of object detection just gets much worse. And the existing state-of-the-art approaches actually do not assume that there could be lossy V2X transmission. This is definitely a serious limitation we try to remedy in this work. Next slide, please. So just a quick illustration of the related work that's focused on collaborative perception. And they all have various limitations with respect to sensing errors, sensor synchronization issues, and lossy network. And the various fusion methods mostly are intermediate fusion, because early fusion, as you can imagine, that it requires sending raw sensing data, which becomes very expensive in terms of the bandwidth consumption. Next slide, please. So what we are proposing is a solution called Scorpion, which stands for Spatial Temporal Collaborative Perception Model on Lossy Network. This was published in IROS this year. And essentially, we have come up with 3 components which help address these limitations. And I will go into details in the next few slides. But just for illustration, as you can see, we have these bird's eye view feature construction. And sometimes you can experience loss. So we come up with a spatial alignment to deal with these kind of lossy patterns. And then finally, we have temporal alignment challenges to ensure that when data connected at different times, we can still merge them effectively to mitigate that temporal misalignment. So next slide, please. So at a high level, we have a component called LBEV-R, and also DSCA and TA. Those 3 components work together. So in terms of novelty, what we have is the deformable spatial cross-attention, DCSA. It basically allows the fusion of multi-vehicle features despite spatial misalignment. And temporal alignment module, TA, helps incorporate historical BEV feature information. And finally, the novel component of construction of BEV feature reconstruction module allows us to guard against potential lost features. So when we are trained on behavior where the network could drop specific feature packets, so that way it can still be able to successfully, with high probability, to reconstruct the features. Next slide, please. So to start with, let me explain how the loss BEV feature construction works. As you can see on the right-hand side, you have features in a given packet. And from the collaborator BEV features perspective, you can experience packet loss, right? So when you do this partial BEV feature reconstruction, we leverage a design called MAE encoder, which is a masked autoencoder design. And this is a previously published paper in CVPR, but we leverage that design for the purpose of training against network packet loss. And this allows us to increase the success of being able to reconstruct the data. So we create these patchified BEV features. So this way allows us to have the decoder recover the original BEV feature by processing the encoder output. So the patchification process basically allows us to reduce the BEV to a few large patches to enable reconstruction successfully. So next slide, please. For the deformable spatial cross-attention, this is another novel component. So here, the idea is that instead of using the standard attention mechanism, this approach interacts with a learned set of the offset points across all the BEV maps. As you can see in the figure illustrated below, we have these different colored points, this multi-head cross-attention. And with the max fusion layer, this allows us to fuse the data, to combine the data together to address potential spatial misalignment. And this helps us to overcome these challenges when we have various localization errors. Next slide, please. So finally, briefly talk about the temporal alignment support. Basically, what we do is to incorporate historical BEV features, and this gives us benefit of creating this spatially wrapped historical BEV map from the perspective of eco vehicle using GPS and IMU sensor data to estimate the location. And this can help us to align the temporal information. Again, we use the max fusion to generate the fused BEV. Next slide, please. I will briefly talk about the evaluation of our system, Scorpion. To start off, we look at the perfect environment setup with no networking loss, no localization or synchronization error using common data sets researchers often use for this collaborative perception solution. As you can see, Scorpion is very competitive compared to previous state-of-the-art solutions. At the bottom bolded color, as you can see, it performs the last one performs slightly worse, but overall it's better or about the same as the previous solutions, state-of-the-art solutions. Next slide, please. So now we evaluate under networking loss conditions, what happens when we leverage the three novel components. As you can see, as the loss rate increases with different data sets, the improvements are over 13, 7, or 3% respectively on these different data sets. The Scorpion solution is the blue line with the dotted circle. As you can see, they always stays on top for the average precision for the 0.3 IOU threshold. Next slide, please.
This one?
Yeah, so this one, yeah, similarly, we evaluated for localization and synchronization errors. So again, Scorpion's solution results come on top, right? So you can see the blue line consistently performs better. Next slide, please. Yeah, so it outperforms baseline given these error setups. So we also have a visualization, as you can see, with the green ground truth and red prediction. It shows that our solution on the right-hand side, the rightmost two boxes labeled as D, it shows that there's the least kind of misalignment between the green and red box. Yeah, it's a little hard to see, but it is something that we also were able to quantify in terms of the errors. Next slide, please. Yeah, as you can see, it highlighted here. This one is, again, a visualization. You can advance a couple more times. For both entrance ramp and curvy roads, it's very close to our original. On the right-hand side, shows that the reconstructed BEV is pretty much very close just by visual inspection. So finally, I have a quick video to show you guys for the demonstration. If you can click on the play link, play, hopefully it will show up. So this is looking at visualization of repaired feature map. And we have different data sets and for different types of scenarios for entrance map. As you can see, there could be some false positives if you don't have fusion support. Based on the Scorpion-based solution, it has much better accuracy. And finally, again, what we are looking for is the red and green boxes are very closely aligned because the green boxes are the ground truth and the red ones are the prediction. Yeah, so I think the video should end fairly soon. Yeah, so these are all different kind of scenarios, urban curvy street, because we want to look at different kind of driving conditions to see how Scorpion performs. And for all these cases, we inject lossy network patterns to emulate realistic network conditions. As you can see, this shows that we definitely have an improvement. So with that, next slide, please. Yeah, so I have a summary slide to describe the contribution for this part of the work. So as you can see, there are several main challenges with respect to sharing data in a collaborative way due to the real-world dynamics. And those dynamics have not been previously carefully studied in terms of spatial misalignment caused by localization error, temporal misalignment caused by timing synchronization error, and finally, the lossy network patterns, which are real because of the amount of bandwidth we have are often limited. So we came up with a end-to-end collaborative perception model design that leverages previous solutions in the computer vision community, but applied in the wireless networking setting to aim for overcoming these errors, and it handles fairly well localization and synchronization errors at the same time, and also is robust to lossy wireless network communication setup patterns. So with that, I will hand it over to Professor Feng to talk about the next topic.
Yeah, thank you, Professor Mao. Next I'm going to talk about our work. I mean, it's a little bit switch. Molly talked about the collaborative perception between the vehicles. We all know that this collaborative perception or the cooperative perception concept is also very critical for the infrastructure applications. For example, we can improve vulnerable road user safety. We can optimize the traffic signals through cooperative perception, and also we can enable other applications like eco-driving to improve the fuel efficiency. Next, please. So similar as the vehicles, right? If we look at this problem from the infrastructure perspective, there's also cyber risks. For example, the infrastructure sensors can also be tampered, or not only vehicle-to-vehicle communication, but also vehicle-to infrastructure communication. These messages can also be spoofed. For example, this sensor data sharing message defined by the SAE. Next, please. So in this work, we actually look into one particular cooperative perception-based infrastructure application is the traffic signal control. So this figure shows a general idea. It's like we have a few CAVs on the road, these green vehicles on the road, and they can not only report the real-time status of themselves, but also to report the surrounding vehicles, their detected vehicles, right? And one CAV will send these detected information in terms of the SDSM and send to the infrastructure side, and then the traffic signal controller takes these SDSMs and then optimize the traffic signal timing. And one benefit of this cooperative perception-based traffic signal control versus the traditional like connected vehicle or trajectory-based control is that this one requires a much lower market penetration rate of the CAVs. Okay, next please. So in this work, we're particularly looking at this the system called the CAV Lite. And due to the time, I'm not going to go to the details of this model, but just the one takeaway of this is a deep reinforcement learning based traffic signal controller. Okay, so use a deep neural network to generate the policies of the control. Okay, so next please. So then our threat model in this case is first we assume a black box attack in which the attacker cannot access the signal controller directly, or the detailed configurations of the CAV Lite model, for example, the neural network structure is inaccessible for the attackers. But at the same time, the attacker can observe or receive the SDSM from other CAVs and also receive the spy data from the traffic signals. This is a reasonable assumption because all the messages are in broadcasting mode. So as long as the attacker can acquire a valid credential, then it basically can spoof into the communication network. And we consider a data spoofing or data poisoning attack where the attacker can fabricate or falsify the communication message in terms of the SDSM. As the figure shows that, like, if we have one compromised CAV and sending falsified SDSM, and then it's mixed with this benign SDSM and feed into the traffic signal controller to make the decision. Okay, so this is our threat model. Okay, next please. So the core of our attack model is called this Jacobian-based silencing map attack, which was first it's a white box attack, and it was originally proposed to attack image classification deep neural networks, like the example that Molly just gave for image classification between panda and goblins. And so the key idea of this attack model is to manipulate some pixels in the picture or some states. Some features in the input, and then to influence the classification results. Or in our specific case, is that to manipulate the traffic states in the input to the reinforcement learning agent and try to manipulate the action of that agent to the target action that we need. For example, if we want to manipulate the traffic signal to extend the phase, or to manipulate the traffic signal to switch the phase immediately, right? So through this Jacobian-based silencing map. Okay, so next, please. Okay, so in order to launch or to implement this attack, actually we need some supporting components. So you can see in the figure that JSMA is in the middle, and on the left-hand side, we need a surrogate model. This is because JSMA actually is a white box attack model, which requires the neural network structures or the parameters, but our assumption for the attacker is the black box attack, right? So the attacker does not really know the neural network structure of the original TSC agent. So what we do is we use this offline training to train a surrogate model to represent the policy from the original TSC agent. So this is more like a policy distillation process, and then we just use the simplified neural network from the surrogate model to feed into the JSMA to mimic this original neural networks. And then another important input for JSMA is the state, so or the predicted state. So in this case, we actually integrate this traffic flow model called the cell transmission model to predict the future state of the traffic, and which is the input for the JSMA. And later I will introduce why we need to predict the future state. And then the third input for the JSMA is a target action. Basically, in our context, whether we want to switch the traffic signal or we want to extend the phase. And to optimize that, we actually train another deep reinforcement learning agent called attack agent to generate this target actions. You can consider this attack agent as a inverse of signal optimization problem, where the original agent as objective or the reward is to minimize the total delay, for example, but here we want to maximize the total delay by generating the target action. Okay, and so then with this surrogate neural network with the predicted state and also the target action, then the JSMA can generate the perturbated state. Okay, and which is this adversary features out of this JSMA component. And then the final step, giving this fake state or the perturbated state, then we incorporated another fake vehicle trajectory generation model to generate these real fake vehicle trajectories out of this fake state to match with this fake state, and then use this generated fake vehicle trajectories to encode them into this fake SDSMs and then feed into the traffic environment to execute. So this is kind of the whole attack pipeline. Next slide, please. Okay, so this slide actually shows the attack timeline, and you can see there's time 1 or state 1 when attack start, and the time 2 or state 2 when the attack ends. This is the duration where we want to generate the falsified vehicle trajectory, because the attacker actually reads the state at time t1 and need to predict the traffic state at time t2. And actually, this time t2 state is the input to the JSMA attack. This is why we want to integrate this cell transmission model to predict the future state so that the JSMA know which is the state at time t2. And then finally, we receive when the attack is launched at time t2, and then we receive the reward even one phase later. Next, please. Okay, and this is introduction of the cell transmission model. I think many of the audience know this is a very famous traffic flow model, where we use kind of a snapshot of the traffic state at T1 to populate the cells in the road network and use the rows in the CTM to deduct the number of vehicles in each cell, the average density and the speed in each cell at time T2, and which this is the input to the JSMA model. Next, please. Okay, and this is the design of the DRL attacker, basically to generate the target action for the JSMA attack. So we use the current state and the CTM predicted future state as the state for this attacker, and the action is to the target action, right, to switch or stay for the current phase, and the reward include 2 parts. One is to change of the delay. Basically, we want to give positive reward when the delay is increased. And also a penalty for the failed JSMA. If the JSMA cannot really generate some perturbated state to launch the attack, then we consider this attack is failed. So we introduce some penalties for this action. And we use the people algorithms and the neural network structure. I'll skip some details. Okay, next, please. And finally, this module is this fake vehicle trajectory generation module, right? Actually, given the perturbated state generated by JSMA, we need to generate these real vehicle trajectories. So we model this as a optimization problem, specifically a mixture integer linear programming problem, to generate all the fake vehicles, like surrounding one CAV with other detected vehicles all together. You can see an example from the right figure, and also during the generation process or during this optimization formulation, we also considered other factors like vehicle dynamics, trajectory relations, safety, smoothness, and so on. The main goal is to make these generated fake trajectories as realistic as possible. Okay, so next slide, please. Okay, so these are all the components in the model. So then we implement this in this real-world intersection in Michigan, and also with this calibrated traffic demand. And you can see in the right figure, right, the red vehicles is the CAV, and the blue vehicles are these detected vehicles surrounding it, and then the other vehicles are these unobserved vehicles. And so if the one CAV is compromised, and then both the CAV and also these blue vehicles are the fake vehicles we're talking about. Next one, please. I think this is a video. Julie, can you play it? Yes, okay, so this is a demo video that we see, and you can see the effectiveness of the attack. You can see it to reduce the length of the through movement of the main street, and you can see try to extend the movement of the side street, signal of the side street, although there are not too many vehicles coming, right, like the northbound as well. Right? And again, try to shorten the through movement phase, and you can see the queue start to propagating in this case. Okay, and next slide, please. Okay, so this is like a initial performance analysis. We compare one is there's no attack. You can see under the original signal, I mean the original A agent, the mean delay is about 50 seconds. And we also compared this with some simple rule-based kind of a rule-based attack. We can increase the delay to about 60-some seconds. And with our proposed attacker, we achieve the highest delay, more than 60% than the original case. And also the bottom two figures shows the comparison, the pie diagram of the signal phase timing distribution of different phases. And you can see with the attack, we significantly increase the length of the side street faces and reduce the length of the main street faces. Next, please. Okay, so as a summary, so in this work, we developed a end-to-end attack model towards a cooperative perception-based traffic signal control system. And our threat model is to compromise the data in the sensor data sharing message. And we show that compromised message or the fabricated messages can cause severe congestion in this case. And also, we think the same attack model not only can be applied to this traffic signal control application, but to a lot of other SDSM-based transportation applications. And so our next step is to develop this misbehavior detection models and the mitigation strategies. Okay. So Julie, do you want to take over, or do you want me to?
Sure, why don't you go ahead? Yep.
Okay, so we just have one very quick conclusion remarks. And although you can see we have 3 different works from different aspects, but actually all of our work are centered on this communication between the vehicles or between the vehicles and the infrastructure in the applications of telecommunication in terms of autonomous driving, in terms of the infrastructure applications. So as a summary, we really think that to tackle this cybersecurity problem in the next generation connected and automated transportation systems, we really need to think from the bottom to develop a holistic and systematic framework, defense framework. I think that's all for us. Thank you very much.
So any questions? We have about 10 minutes. Yep.
Yep, we'll get started with some questions here. All right, so the first one we have is for you, Professor Zhang. Thank you for sharing your research. This is a 3-part question, so we'll do the first one first. What kind of cryptographic mechanism is used for the watermarking of the video frame in this research?
Right. So here we're actually just using the kind of standard the symmetric key AES kind of mechanism, because we have a sessions that kind of set up. We can exchange the shared key, so that by kind of just encrypt some watermarking, that's very little data, so we don't have to encrypt in the entire kind of video frame, which is going to consume a lot more time.
Okay. And the second part to that question is, how is this watermark being verified in teleoperation? And which of the stride threats are the primary focus in your research?
Right. I mean, the part is that the teleoperation part, we can decode the data. We have the timing information, right? So we use that both to calculate latency, but also we encrypt, kind of include a secret key using random sequence number to kind of move that ahead. So the challenge, obviously, you may have some of the frame that may be actually lost or data lost, you cannot decode it. So essentially we have a kind of a random sequence number. We're using information what we have received in the past. to say, hey, if you have someone just say to replay it or inject some random frame, we can actually reject those images.
Okay, great. And the last one is, can MITM replace the frame and create new watermark that seems correct to the teleoperator side?
What is MIIT?
Yeah, I'm not sure. They just wrote MITM. Maybe if you're still on.
Right, and we use the term watermarking as a generic term. It's not kind of related to traditional kind of image watermarking that for copyright
looks like it's
purpose,
man
right?
in the middle.
Right. Oh, yeah. So that's where we're assuming someone might be able to inject just randomly sending some data to disrupt your pipeline.
Okay, great. And then our next set of questions is for Professor Mao. So the first part, can you please elaborate how lossy network is addressed? Did you use a redundant network path? If you're still here, Morley. And you're on mute, just so you know. You still with us, Morley? Okay, all right, we'll move on to the next one, and then if she comes back, she can answer these questions. This is more of a general cybersecurity question. What mechanisms can be established to harmonize industry standards globally to ensure consistent cybersecurity resilience across the CAV ecosystem?
So could you repeat the question just one more time?
Absolutely. What mechanisms can be established to harmonize industry standards globally to ensure consistent cybersecurity resilience across the CAV ecosystem?
I mean, this is really a good question that we don't really know the answers right now. We still starting from where bottom, right? So for try to come up with the standardization, probably there's some basic thing that would be kind of secure, right? Depends on whether we talk about CV2X, for example, some of the basic things I know industry are concerned about, also some of the supply chain, how do we actually authenticate? So in the CV2X, we already have the SEMS system being established to authenticate the messages, right? So some of the research we are looking at, especially what Molly and Yiheng is looking at, more kind of forward-looking, more kind of explore the problem of attack on the machine learning model itself, and how to actually secure that one. That one probably not going to be standardized yet, because I know from the practical point of view, there's a lot of constraint on the wireless capacity. So I know the SDMS currently talk about actually not even at the intermediate feature exchange, but more on the result. You detect a particular object, then exchange that object itself, right? So again, for example, I believe in order to do this kind of harmonize all the kind of system is you need to have some kind of way to synchronize the state, right? How do we make sure the time information about all the vehicle going to be actually synchronized? Because otherwise, you send the data, you have only your time, you actually have no idea when that frame or when that data is sent, whether they're obsolete. Should I discard that messages because that message was sent has completely obsolete, right?
So
Right, thank you.
I'll quickly add to that. I mean, like Julie mentioned, under the current, for example, the current SCMS system has a misbehavior detection module. But as more and more attack vectors appear and more applications, new applications, I think, for example, this module also need to be keep developing to adapt these new attack types and applications.
Thank you. Our next question, where do attacks against AV detection systems generally originate, and what's the purpose behind those attacks?
So, you want to take Nasha Monty's back or not?
Yeah, I think there are a lot of, I mean, incentives, right, to have some personal gains or some even more severe, like some terrorist attacks. or some may gain some financial benefit and so on. So there are a lot of incentives behind all type of cyber attacks.
So it's the question about where such an attack against AV originate from, right?
Yeah, where does
Right.
it originate is the first
Right.
part.
I think for me, at least there's two major sources, right? So I mean, three, for example, someone can having their own malicious vehicle, the purpose is want to disrupt the whole system. So that part, they basically they have their own malicious vehicle. The second part, I mean, people can attack autonomous vehicle if you park somewhere, for example, robot taxi, someone could potentially can tamper the LiDAR camera or install something. Those are a lot of things would be the vulnerability from the autonomous vehicle itself, right? So CAN bus system, for example, like even the research vehicle we have today doesn't really have a security mechanism. We can just plug in another device into the CAN that can disrupt. And the third part is the kind of similar to that one. You have a cyber attack. Someone may be actually insert a device which you have a wireless connectivity, then cyber attacker can be then control that particular vehicle.
Excellent, thank you. All right, we have time for one more question. And so this is more about autonomous driving and traffic control. What do you think about the relationship between autonomous driving and traffic control? Should they be realized in decentralized or coordinated ways?
So I think they should be coordinated. There's a lot of research in our field how to coordinate, for example, the traffic control and the plan of the connected of the autonomous vehicles trajectories at the same time simultaneously, developing some integrated control model where like the traffic controller serve as the master or a high level controller, and then to guide the behavior of the CAVs. And actually, a lot of research have shown that this joint control, integrated control mode, can achieve better system performance in terms of both safety and mobility.
Excellent. Thank you. All right, that's all the time we have for today's CCAT Research Review. I want to thank Drs. Feng, Mao, and Zhang for taking times out of their busy schedule to be here. If you're interested in learning more about these projects, you can explore this and other research led by those three universities on our website. The links can be found in the chat box. The final report for this project will be available soon. We were actually just talking about that before we went live. And you'll be able to read it in its entirety by going to the website linked in the chat box as well. Finally, if you missed any part of today's presentation, it will be uploaded to our YouTube channel on Tuesday, December 9th. Please be sure to subscribe and click on the bell to receive notifications. Thank you all for joining us today, and we hope you have a great rest of your day and have a happy holidays. Take care.
And if anyone have any specific question, feel free to contact us also.